Okay, let's get started, please. So let's just start off with an exercise. So we talked about convergence the other day, and there were a bunch of implications of convergence, and they're all pretty straightforward. So I'd like you to try to prove at least one or two of them. So you have a sequence in XD, a metric space, and so the claim is that if P sub n converges to some point and P sub n converges to some other point, then those points must be the same, right? In other words, that the limit of a sequence has to be unique. Okay. So start off thinking about that. Think about it for, say, 3 minutes or so, and see if you can, explain why those things would have to be the same. Right? And so remember, P sub n going to P means this thing that, given any epsilon, there exists a delta, there exists an n, such that if you are past n, then the distance of P of n to P is less than epsilon. Right? The picture being that, you've got this ticker over here, right? And you've got your space, and you've got your point, right? And given any neighborhood of P, there's some time past which everybody lies inside that neighborhood. Okay? There's got to be some time where everybody lies inside the neighborhood. Right? So given any epsilon, we start from here, to there exists an n such that everybody above n, right, that if you're above n, then you lie inside that epsilon. So I want you to think intuitively, and I also want you to think rigorously. So intuitively, you want to have some feeling of what it means for the limit to be P, right? So it means that you can make your sequence, excluding a finite number of guys, you can make your sequence as close to P as you want. Right? That's what the limit being P means, right? That basically everybody is close to P. Right? So if I say, I'd like you to say within an inch of P, well, excluding some finite number of guys, everybody is within that inch, right? And that finite number may be a billion, right? But even so, there's still, the infinite the infinite tail end of it is all within that inch. Okay, talk to your neighbor for a second and just say, like, this makes a lot of sense, or this, why would this make sense? Molly, why don't you talk with Andre behind you? Andre, talk with Molly in front of you. You guys talk. Okay, somebody want to tell me about it? Like, why does this make sense? If you've got two points to which the sequence converges, then they must be the same point, right? Why did that make sense? Oh yeah, Max.
We can think about the neighborhoods with radius of half the distance between P and P prime.
Okay.
And then those two neighborhoods of P and P prime respectively won't intersect.
Okay.
But you're saying that every point after a certain n has to be in both.
Okay, so you're going for a proof by contradiction. You're saying, suppose there are actually two separate points, right? If there's two separate points, then there's a definite non-zero distance, right? There's a definite positive distance between them. Take half of that distance, right? So there's a definite positive distance. Let's take half of that distance, right? Well, we know that, by convergence, everybody's got to be, within this neighborhood, right? But by convergence, everybody's got to be within this neighborhood. That's impossible, right? If there are two separate points, that's not possible, right? So you could do a proof by contradiction. Let me give a slightly different proof. You can say, like, what is the distance between P and P prime? Let's think about that distance between P and P prime. Okay. So fix an epsilon. Fix any epsilon, right? So fix any epsilon. And suppose this is P, and suppose this is P prime. I fix an epsilon. Okay. Right? And fix any epsilon, I know that there exists a time such that past that time, at the distance of my xn, the distance of Pn to P is smaller than epsilon. Right? And I also know there's a second time, n2, such that if we're past that second time, then the distance of Pn to P prime is less than epsilon. Right? Okay. So it's tell me, right? Well then, for n exceeding the greater of those two, we know that the distance of Pn to P is less than epsilon, and the distance of Pn to P prime is less than epsilon. And so the distance of P to P prime by the triangle inequality, right, is less than or equal to the distance of P to Pn plus the distance of Pn to P prime, right, which is less than 2p. Yeah.
When we say the distance between P and P is less than epsilon, can we use can we say then that like the absolute value of Pn minus P is less than epsilon, or are we
if you're in Rn or Cn or something like that,
Oh,
right?
we're
If you're in we're not in Cn, right? We're just in a metric space.
Okay.
Yeah.
Okay.
So you want to use G, the metric, rather than absolute value metric.
Okay.
Yeah. But it is sort of true that almost any argument you can make in Euclidean space it's still going to work. Just change everything to d's. Yeah. Okay. So what does that tell me? Actually, let me make this a little bit cleaner looking by saying that I'm going to divide my epsilons by 2. So that I get an epsilon here. So I fix my epsilon. I know there's some time past which everybody's within epsilon over 2 of p. Everybody's within epsilon over 2 of p prime, right? And so the distance from p to p prime is less than epsilon. Okay. Well, what does that tell me? That given any epsilon, the distance between p and p prime is less than epsilon, right? For all epsilon, the distance between p and p prime is less than epsilon, right? Well, the only way that can happen is that the distance between p and p prime is 0, right? If it's less than every positive number, right, then it's got to be 0. Right? We don't have any numbers that are less than any positive number in the real numbers, right? And there are number systems where there are things smaller than every positive number, but not for the real numbers. Okay. Well, and you know by the properties of a metric that the only way that this is going to happen is if p and p prime are the same, right? By properties of the metric. Okay. So, right, so they have to be the same guy. Okay. So there's another way of thinking about it. You say, well, look, right. I know that for every epsilon, there's going to be some point that lies within epsilon over 2 of this guy and epsilon over 2 of that guy, right? Well, that means that the distance between them must be smaller than epsilon, right? So for every epsilon, these guys have to be within epsilon of each other. Well, they must be the same point. Okay, questions? Okay, so let's go on. So there are a couple other simple facts, simple consequences of convergence. Okay, so this was actually number 2 in the theorem that we call implications of convergence. Implications of convergence. The first one was that contains all but finitely many values. Okay. Number 3, that Pn converges when Pn is bounded. Okay. Remember what bounded means? What does bounded mean in a metric space? What does bounded mean? It means that there's some big neighborhood that contains everything, right? There's some neighborhood that contains everything. Okay, so let me just sketch out the proof, right? So you say, well, fix an epsilon of 1, right? Here's p. Fix an epsilon of length 1, right? You know that all but finitely many guys lie inside this neighborhood, right? So there's only a finite number of guys outside, right? There's only a finite number of guys outside, and so, right? Or maybe there's nobody outside, right? So they could be all inside. In any case, so you say let R be the maximum of the distances of 1 and the distances of P to the guys who are outside. Right? So call these guys Pn1 through Pnk. Let me add on 1 just to be safe. which case I don't need this one. Okay. So take the maximum distance, right? Take the maximum of the distances to the guys outside. And then add on 1. Right? Then add on 1. Or 2. No, 1 is fine. 1 is fine, sorry. 1 is fine, sorry. Okay. Okay. And then you see that everybody lies inside that neighborhood, right? Right? Because everybody lies either within the 1 ball or, within the greatest of these distances. So this is the idea. Right? Okay. Right. Okay. Yeah. Okay. The reason I just want to sketch some of these is because I want to do some other ones that seem trickier. So number 4 was if you have some subset of your metric space and P is a limit point, then there exists a sequence P sub n E such that the limit of the P sub n's actually is that P. Okay. So you have your space X and you have some subset. Okay. So these dots are my E. Okay. These yellow dots are my E. And then there's some point P, let's say this guy P is a limit point of that set. And I want to say that, so these guys are, P1, P2, P3, whatever, okay? I want to say that that guy is, I can find a sequence, no, what am I doing? They don't have any numbers on them yet, right? We're going to make the sequence. I want to say that I can find a sequence of points in this space that converge to P. Okay. Well, what's a limit point? Right? What's a limit point? What does it mean for P to be a limit point? Every functional neighborhood, right, contains a point, right? So you say, okay. So we construct P sub n as follows, right? Fix epsilon to be 1 over n. So let epsilon be 1 over n. Okay. Now, let me say it this way. For each n in the natural numbers, since P is a limit point of E, we know that there exists, we know that the intersection of the punctured neighborhood of P with E is not empty. Right? Here's our P. We know that if I take a radius of 1, there's somebody in there from E. Right? If I take a radius of a half, there's somebody in there from E. If I take a radius of a third, there's somebody in there from E. And so on and so forth. Right? So let E sub n choose and E sub n in that intersection. Right? Right. This guy, you can choose somebody from E who is within distance 1 sub n, 1 over n of P. right? Right. Then the limit of each events is p. Yes, p goes n goes to infinity. Lamra, do you have a question?
No, I had.
You have a
So, if P and Q were both limit points of E, would that still apply, and would only one of them be what the sequence converges to, or?
Well, you'd find different sequences, right? There'd be, like, maybe there's some other point Q, that guy's also a limit point, right? But that would be the limit point of some other sequence, right? So all this isn't saying too much. All this is saying is that if you have some set and has a limit point, then you can find points that converge to that limit point. You can find a sequence that converges to that limit point, right? Let me say something really dumb, which is that if P is in your set already, then this is kind of silly, right? Because you could say, I'm going to take P1 to be P, P2 to be P, P3 to be P, P4 to be P, and the limit is P, right? Okay, so that would be very non-interesting, right? So, right? But even if P is not in E, the fact that it's a limit point ensures that there's somebody else nearby that you can choose and make a sequence that converges to P. Okay, so this sort of leads to the remark that if the limit of P sub n is P, so that the limit of a sequence need not be a limit point of, right? A limit of a sequence need not be a limit point, right? Because you could have a sequence that's just all the same values, right? Right? You can have a sequence like a sub n equals 1, right? 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, right? So it's just a single point there. Well, that's not the limit. That's not a limit point of the set of images, right? Of the set of images. Okay. Let's go on. Okay. Does this make sense? Yeah, Abel.
Would it necessarily work the other way around?
No. So that's sort of this point here, right? That if you have a sequence whose limit is P, it doesn't imply that P is a limit point, right? Because you could have just a constant point. Yeah. Right. Or you could have no. That's right. Okay, so let's go on. So that was facts about convergent sequences in metric spaces. Now we're going to talk about convergent sequences, in the complex numbers. Okay, and my theorem should be called maybe convergence and arithmetic. Convergence and arithmetic. So suppose that Sn converges to S and Tn converges to T in the complex numbers. Okay. Then, as you expect, the limit of the sequence made from the sum turns out to be the sum of the limits. The limit of some constant times S of n is C times the limit. The limit of a product Sn Tn is the product of the limits, and 1 over the limit of 1 over a sequence is 1 over the limit of the sequence as long as S is non-zero and all S of n are non-zero. That's actually more than you need, but we're just going to assume it. Tell her. What, it looks like you can't read something. What am I? Yeah, okay. Okay, so I'm not going to prove the first two. The first two are pretty straightforward. Let me do the more interesting ones. So number 3, we want to show that the limit of Sn Tn is St as n goes to infinity. Okay. So the way you want to think of these results is that they are commutativity results. That is, you can change the order of something. Right? Commutativity means you can change the order. You can do this first, right? You can either go up the stairs and go down the hallway, or you can go down the hallway and then go up the stairs, right? You're going to get to the same place, right? So here, what this is saying is that you can add these guys first and then take the limit, or you can take the limits of each sequence and then add them, right? This is saying that you can multiply the sequence by a constant and then take the limit, or you take the limit first and then multiply by a constant, right? You can either multiply them and then take the limit, or take the limit and then multiply them. Okay, so these are order of operations things. It doesn't matter what order you do them in. Okay. Okay, so we want to show this equals that, which is the same thing as showing that this minus that is 0. Okay. Okay, so we rewrite this as the limit of Sn minus S Tn minus T plus S Tn minus T plus T Sn minus S as n goes to infinity. Okay, right, your picture is, you have, this is not exactly right, but it's close enough. You have some S, you have some Sn, right? Right. So this is pretending that we are in R, okay, which we are not. Okay, you have some S value, you have some Sn, right? You have S, Sn, right? You have some T, you have some Tn, right? And you're looking at Sn Tn, which is this whole thing, right? Sn times Tn is the whole thing, and you're subtracting off S times T, right? What do you get? Sn minus S times Tn minus T, right? You get this guy. You get this thing plus S times this plus T times that, right? So it's just an area statement. Okay, why do we do that? We do that, all right.
Sorry, so you're taking the limit of that entire expression?
Yes. Okay, so why do we change this? We change this because we want to invoke the previous result, right? We want to use the previous result, like S times Tn minus T. Tn minus T goes to 0, right? So we know that this is going to go to 0, right? T times Sn minus S, we know that that goes to 0, right? Right, by the previous result. And then we use the other previous result to say that, the limit of the sum is the sum of the limits, so we can take these limits separately, right? So this thing is going to equal to the limit of Sn minus S, Tn minus T, plus S times the limit of Tn minus T, plus T times the limit of Sn minus S. right? And here we're using the first and second parts of the theorem. Okay. Okay. And we know this is 0, and we know this is 0. Okay. So it suffices to show that this thing goes to 0. Okay. So we want to show that this thing is 0, and how do you do it? You say, well, fix epsilon, right? Right. We want to show that there's a time past which this thing is smaller than epsilon, right? So it's easy enough. You say, choose n1 such that if you're past n1, then the size of Sn minus s is smaller than epsilon, I'm sorry, the square root of epsilon. Right? Choose n2 such that if you pass that guy, then the size of this thing is smaller than the square root of epsilon. Right? And thus, if n exceeds the greater of n1 and n2, we know that the product is smaller than epsilon, as desired. Yeah.
And the limit as n goes to infinity of Sn minus st equals 0, are there parentheses around the whole thing, like Sn minus st? So like the second step of the equivalent,
Here.
is the st separate from the first expression? Like, is it a separate expression, or is the limit applied to both terms?
It doesn't matter. It doesn't matter.
Oh.
It doesn't matter because this is a constant, right? So if you're looking at the limit of something, right? If you're saying that the limit of this minus that is 0, or the limit of this minus that is 0, it's actually the same statement.
Okay,
Yeah.
thank you. Sorry.
Why is there a strict inequality here when n is strictly more than the tolerance? The time, my bad.
Right here?
Yeah.
It doesn't matter. If you want, I can move it.
Okay.
Yeah, that doesn't, in the definition, if you think about it, it doesn't really make much difference. If there is an n such that, at that n and past that n, my condition is satisfied, then certainly there's an n past which that condition is satisfied, and vice versa, right? So this actually is not a significant thing. Yeah, some things are very significant. This one actually has no significance. Okay. Let's do the next one. So number 4. So again, I know these aren't the most exciting things, but they're kind of illustrative. So we want to show that this thing. We want to show that that the limit. We want to show that the limit of 1 over Sn is 1 over s as n goes to infinity. That's the same thing as saying that the limit of 1 over s of n minus 1 over s is 0 as n goes to infinity. Okay, and that's the same thing. If you're showing that the limit of something is 0, that's the same thing as showing that the limit of the absolute value is 0. Okay. Right. So I think this might have been assigned as an exercise, or maybe I will assign it as an exercise. If the limit is 0, right, showing that the limit of a sequence is 0 is the same thing as showing that the limit of the absolute value of the sequence is 0. Okay, so let's think about what that means, right? That means that for any epsilon greater than 0, there exists a time such that past that time, 1 over s of n minus 1 over s in absolute value is less than epsilon, right? Right, this is what we want to show. Okay. Now notice, we make a simple calculation, right? 1 over s of n minus 1 over s is the same thing as s of n minus s over Sn times s. Right. We want to show that if the limit of the s of n is s, then the limit of 1 over s of n is 1 over s. Okay? Okay. So we want to show that this thing is small, right? We want this thing to be small. Okay? So I'm going to say something I'm going to say something wrong. Okay? So you think, okay, well, we can make this thing as small as we want. Right? Sn goes to s. So we can make the difference as small as we want. Right? So choose n such that if you're past it, Sn minus s is smaller than epsilon times SNS. Okay. What's wrong with that? That's actually not the way to go. It's almost the right to go, but it's not quite right. The trouble is that Sn is moving around, right? Sn isn't a constant, right? So you can't say, I'm going to choose an n such that everybody past that n satisfies this condition, right? Because this is a moving target. Right? As your n changes, this thing is changing. So you can't do this, right? This isn't what convergence means, right? Convergence means you can make these guys, smaller than some constant, right? But not that you can satisfy this sort of this equation. Okay. But on the other hand, you do know that S of n is getting close to s. Okay, so what we do is we say, so we just fix it up a little bit. Okay, so so here's what we're going to do. Well, choose n1 such that if n is bigger than n1, then the distance of Sn to s is smaller than a half s, smaller than a half the absolute value of s. Okay. So let me give you the idea. The idea is this, right? That this thing is moving around, but eventually we can basically say the S of n's converge to s. So I can basically say this is basically s. Now it's constant. Okay. Now it's constant, and so I can say choose an n past which this thing is smaller than that, and then everything works out. Okay. So that's not exactly true, right? I can't assume that it's actually equal to s. But I can make it close enough to s, right? So what I'm saying here is that I'm going to choose a time past which this guy, the distance, right? So suppose this is my s, 1/2, 3/2 s, right? I'm saying that I can choose it so that Sn is in this range. It's effectively s. It's not exactly s, but it's basically s, right? It's between some multiple of s and some other multiple of s. Okay, so that's the idea. Right? Say choose, right? And then then this argument can be pulled off. Okay. You say, okay, well choose n1 such that Sn is rough, so this is make Sn basically S. That's our first move. Okay. And then choose N2, such that if we're past N2, we have that Sn minus S is less than a half absolute value of S squared times epsilon. Okay. Then, for n that exceeds the max of those n1 and n2, we see that the distance between 1 over S and 1 over Sn, well, this thing on the top is smaller than 1/2 absolute value of S squared times epsilon. This thing on the bottom is greater than 1/2 absolute value of S, right? So greater than 1/2 absolute value of S times the absolute value of S, right? And so we get epsilon.
Get the denominator.
Okay, so we have so let's suppose that what's the size of Sn? What's the size of Sn? Well, we know that the distance of Sn to S is smaller than half the. Just for simplicity, let's assume that S is positive. Okay. We know that the distance from Sn to S is smaller than half the size of S. Right. So this is S minus the half size of S, S plus half size of S, half of S. Right. We know that S of n lies inside there. Right. So that tells me that S of n is bigger than half of S, right? S of n is bigger than half of S, right? And so that tells me that 1 over S of n is smaller than 1 over half of S. Okay, so I've taken my Sn here and then replaced it by 1/2 of S. Okay, 1 over Sn, if I this thing is bigger than that, so the reciprocals are going to be greater, right? They're going to have the opposite relation, right? So this guy turns into this guy, and this guy just stays as is. Okay, is that clear? Everybody all right? Any questions? Okay. Okay. So maybe that's all I want to say about convergence of sequences. Yeah, that's enough. So there are a couple of results about sequences in Euclidean spaces, right? If you have a vector sequence. But basically what that boils down to is the limit of a vector sequence is a vector if it happens component-wise, right? If it happens component-wise. So if in each component you get the components of the limit, then the limit is actually that thing. So I don't want to, it's not, it's It's not that interesting. Let's instead go on to something really important. So subsequences. It's only 3 minutes. So let me just state the results for the vector part. Okay, so why we don't need to charge ahead. We're okay. We're doing okay on time. Okay, so okay, it's not particularly interesting. Sequences in okay. Sequences in Euclidean space. Okay, so suppose you have be a sequence of points in space. Okay, so you've got these exabends. Right? Each of these is a vector in Rk. In other words, a point in space, a point in Rk, in Euclidean space. Let's say that exabend is alpha n1, alpha n2, alpha n2, alpha n3, alpha nk. Okay. Okay. And let x be some vector alpha 1 to alpha k in Rk. Then, like I said, it's not particularly interesting, but then the limit of the vector sequence is this vector if and only if it happens component-wise, right? If and only if the limits agree component-wise, right? In other words, the limit of alpha and I equals alpha.
Why did we change that to B instead of O? No.
Okay. Equals alpha I as n goes to infinity. Right. All this means is that just look at each component, right? If the limit of the first component equals this guy's first component, and et cetera, then the limit is that vector. Okay. For I equals 1. Okay, and then similarly, you have results like the limit of a sum of these things is the sum of the limits. The limit of the dot product, x sub n dot y sub n, is the dot product of the limits, etc. Okay, so results like this, but they're not. It's not particularly interesting. Yeah, Max.
Would that also be true for cross product?
Yes. Yeah. Okay.